Good morning, and welcome to the panel discussion on driving efficiency in AI infrastructures. I'm Suresh Vasudevan, CEO of Clockwork Systems. Clockwork is a pioneer of software-defined fabrics, fundamentally a software platform that addresses what we believe is one of the most significant barriers to AI infrastructure efficiency, which is really the effectiveness of communication between GPUs. Several cloud providers, including one of the leading hyperscalers globally and many NeoClouds, as well as large global enterprises, have deployed Clockwork to drive 25% greater cluster utilization and to drive fault-tolerant training. Today, I am really excited to have with me a group of panelists that I think will bring great insight to bear, deep expertise, domain expertise, as well as lots of wisdom to share as we talk about what it means to drive efficient AI infrastructure deployments. With me first is Dylan Patel, founder and chief analyst at SemiAnalysis. Dylan has become one of the preeminent voices in decoding the complex world of AI infrastructure, all the way from silicon to large-scale data center factories, AI factories. SemiAnalysis puts out extremely incisive, thorough and detailed analysis on everything from upcoming technology developments all the way to how AI data centers work. So welcome, Dylan. Joining Dylan is Neil. Neil Pinto has been a leader at LinkedIn for 2 decades, driving infrastructure engineering at LinkedIn until very recently. In particular, with respect to AI, Neil and his team have deployed thousands of GPUs across multiple data centers, and so he brings real frontline experiences to bear on the topic of how to make AI infrastructure pay off and deliver ROI. And joining our panel is Jack. Jack is CTO and VP of Advanced Technology at SHI and leader of the state-of-the-art AI lab at SHI. Jack, your team of engineers and architects work with a large number of leading global enterprises in doing everything from early stage concepts all the way through to production rollouts. So thank you very much, all of you, for joining us. I'm looking forward to what I think will be an extremely lively discussion. Let me start by setting a little bit of context on what it is that we're talking about. Everyone sees the large numbers. There are billions and billions, tens of billions, hundreds of billions being deployed in AI infrastructure. Hundreds of megawatts of energy being deployed to drive AI factories. And yet, study after study shows that utilization, overall cluster utilizations in large-scale GPU clusters run at 30 to 50%. And when you think about the economic cost of that waste, it's staggering. As you peel the onion, it seems there are 3 broad sources of inefficiency. The first, measured through GPU allocated utilization, is really about if I were to spend on 100 hours of GPUs, what percentage of the time is my software actually running on those GPUs? So things like hardware reliability, software reliability, scheduling inefficiencies take away from GPU allocated utilization. The second inefficiency is measured in what's often termed as effective training time ratio. So if I have X hours available when software is actually running on those GPUs, how much of that time is spent by the GPUs in doing actual computation versus waiting? So things like latency in the network, things like latency in loading data, ineffective communications all come in the way of effective training time. And the last source of inefficiency is really around model flops utilization, which goes to the heart of model design itself. So for example, if I'm doing lots of small matrix multiplications, I'm not getting to the theoretical capability of the GPUs. So as we step back, that's just a broad framework to think about what is driving the overall utilization being 30 to 50%. But now let me just switch to first talking about the importance of infrastructure efficiency in driving overall ROI. And maybe I'll start with you, Neil. You've at LinkedIn, you've watched the deployment of AI to achieve certain business goals. I'm curious how you might have defined the business goals and how you translated those into what it means for infrastructure.
That's a good question. So, I would, before getting to that, the GPU AI strategy, matured over time. It's not something which happened day one. And we've been at LinkedIn always been using machine learning and a lot of the machine for recommendations in the product over time. So this is something which evolved over time. We were initially basically working with V100s, the A100s, and life was going on as usual. We were deploying them at a particular regular deployment schedule, and capacity was being made available. But when ChatGPT came out in 2022, that changed the whole game. Engineers and product folks started thinking much bigger what LLMs can do, and that opened a floodgate of different ideas and creativity in terms of what was needed. Being the infrastructure guy, every morning I would come in and there would be, hey, we need so much more capacity. There was like tons of requests coming in every day. And we hadn't planned for this kind of sudden change in the technology. So part of the things that I got stuck with and having to make sure that we could deliver, one was on providing the H100s. They were, when they came out H100s. There were still supply chain challenges getting H100s. The next big thing is like the data centers were all set up for, rack density of, we would support 96 servers, and they probably pulled 25 kW power. These things were, power hungry and hogs that they needed more power. So we had to kind of figure out what we need to do with that. On the network side, we had to think about, when we did the A100s, they were all NVLink within the server. This was now talking node to node, so NVLink and coming up with InfiniBand, so that was a whole other thing to do. But all these things came, so the first 6 months, I would say, was a little bit of a cluster. Everything was like a bunch of stuff happening at the same time, making promises, supply chain challenges. But over time, it evolved into, once we had a very well mapped out infrastructure plan and allocation, these things cost so much. They cost like gold. So we had to come up with a kind of strategy about who got allocation, which teams or which products got actually ROI and turned it into revenue. So we kind of came up with that. From the infrastructure standpoint, we came up with actually a roadmap in terms of how we deployed. At the time, we were deploying 1,000 GPUs at a time. I know now people are deploying gazillion GPUs or whatever. But at that time, we had to come up with a methodology in terms of what we deployed, who got what. Once we did that, we then started to realize that these GPUs which were being allocated were not being utilized as much. Like barely you were getting 20% utilization. That is also negotiating with the teams that they were making that much. So I think what is key for us to is start to provide observability, start to get information about how the GPU is being utilized, what the workloads and that kind of stuff. We had to bring that out. And then also another thing that we realized was orchestration of jobs. Most of the time, these jobs are waiting in queues, which were built for big data systems. They were not really utilizing the GPUs as much. And so it became apparent that the data which we were pulling from HDFS and Hadoop systems, running on spinning drives. So it meant bringing the data closer, running them on much more, staging the data so that it could be sucked into the GPUs. And I always call the GPUs like feeding the beast. You want to make sure that you're continuously feeding it so they're kind of utilizing. And that allowed us to move the needle more in the direction of utilization. So I think all these things have to come together. Observability, utilization, and orchestration are key things for bringing, and so that's how we started getting more into a rhythm. And now we had deployed about, I think, 15,000 GPUs across 4 data centers.
Fantastic. Just to paraphrase, so it's almost when I asked you what were the business challenges and how did they manifest into infrastructure, what I hear you saying is the first phase was just actually supply chain, deployment, operationalizing. And after that, it almost became, how do I measure how efficiently it's being used? How do I orchestrate the provisioning of those resources to various teams, and who should get how much? And sort of almost then it became a process of driving utilization. Very, very helpful. Dylan, I'm going to shift from enterprise for a moment to NeoClouds, right? So more and more companies are relying on NeoClouds as the experts at provisioning GPUs and providing that in a manner that's easier to get going versus having to go down the LinkedIn path of deploying everything from the ground up, right? And yet it feels like there are a lot of NeoClouds and they're operating on razor-thin margins. And so as I think about what differentiates good NeoClouds from maybe ones that may struggle from a business model and profitability standpoint, what is the role of infrastructure? How do you think about the business model of these NeoClouds and linkage between sort of successful NeoClouds that are able to be profitable and what they have to do at the infrastructure layer?
Yeah, so the NeoCloud industry is one that's quite dynamic and new, right?
Right.
And within the last 3 years, there have popped up 200 NeoClouds. Whether they are directly deploying the infrastructure themselves, that's 160 companies, and then another 40 or so companies that are taking capacity from various places and trying to offer it to customers. So you can today go out and rent GPUs from 200 different companies, which is absolutely insane.
It is.
And these things are not simple, right? On an infrastructure standpoint, there's all these complexities around deployment. These are very expensive, very hot, very power hungry. The networking is complicated. All of these things apply. Their failure rates of GPUs are super high,
Right.
And so you have to be able to service them. And that's something that is not something most infrastructure organizations are initially set up to do. So you have all of that, and then on the flip side, you have 200 people doing this, so there's so much competition and so much. To evaluate the NeoCloud industry, we created this benchmark called Cluster Max, where we review all the NeoClouds as well as the hyperscalers across 9 different metrics, right? Whether it be lifecycle management, reliability, networking, security, performance, and all these various other metrics. And what's really differentiated the NeoClouds. We first created this metric in the beginning of the year, and since then we just released the second version. But in the middle, the clouds that ranked the highest actually ended up booking way more revenue, right? Whether it be with the OpenAIs of the world, or Microsofts or Metas or other labs, right? Or startups. And so what's interesting is what separates these NeoClouds is their ability to deploy the GPUs faster than anyone else, right? This is a race. The more time you have having paid a PO and not having the GPUs running is money being wasted, given the useful life of these GPUs is 5-6 years at most. And so 3 months delay is a lot of your useful life, a lot of your profit. Another one is the ability to actually reliably get them up, right? These GPUs have pretty stringent SLAs, and any downtime ends up being time that you have to credit back to the customer and money that's lost. And also, reliability problems spread around and you get less customers generally. And then the other one is performance, right? Customers are often running a POC before they sign a multi-hundred million or billion-dollar contract. They're actually running a POC on a cluster that's worth $1 million or $2 million of rental time from the cloud to validate that the performance is there, whether it be networking, CPU, memory, storage, etc. Outside of just the base GPU. And then lastly, sort of there's all this around what software do they want on top, right? Sure, some customers are okay with bare metal, but more and more customers want to manage Solar, manage Kubernetes now with the advent of RL. There's companies that are there's NeoClouds starting to offer managed array services. So these services that you layer on top, not necessarily, hey, API inference or an actual like RL or fine tuning endpoint, but rather, hey, what is the infrastructure software that's required to manage this, make it simpler to run, make it so the NeoCloud can run health checks in the background, right? Both active and passive health checks. When you have idle cluster time, run active health checks. When you don't, be running passive always. Doing advanced, before any failure happens, predictive maintenance, right? So you're managing SLAs better, right? You're like, oh, okay, I'm at 99.5% uptime right now. Let me take this node down because we think it's going to go down in a day or two. And then that way you stay above your SLA and never credit back the customer. And this has enabled, the top in the industry companies to have gross margins of 35-40%. And now there's a ton of NeoClouds that are losing money. There's I believe 5 or 6 that have already gone out of business. And it's only been a few years, right? So this is a cutthroat world, and we think that the NeoClouds need to be really smart to actually make it.
So that is a massive spread. So really, and I want to just play back some aspects, right? So the best performing NeoClouds operating at 35-40% gross margin, all the way to negative gross margin for those that probably lack the same discipline. And some of the things you call out, which is actually I want to pivot from one of the things you called out to you in a moment, Jack, but you talked about you lose gross margin if you take a long time to deploy because you're eating into the useful life of the GPU itself. You lose time when reliability takes your systems out of action, if you will. And so any failure is basically lost time that you could be renting GPUs for. And it's also loss of reputation with other customers that may not come to you. It feels like you lose some time. This I did not realize, but also you lose some amount potentially in POVs that may not then ultimately scale to production. So how do you handle POVs and make them successful is one. And then, of course, the operational management around driving utilization, making sure you're preempting failures and letting the customer get sort of a good service level, if you will, or almost day-to-day operational stuff as well. Interesting. And that spread is massive. The 35 to 40% gross margin spread is massive, and I can clearly see how infrastructure plays a role. I just want to pick up, given what you do, Jack. You have this massive state-of-the-art AI lab where you're putting a lot of mainstream enterprises, or you're helping mainstream enterprises run experiments, run POVs, and then scale that to actual production deployments, sometimes on NeoClouds, as I understand it, sometimes on hyperscalers, sometimes in their own data centers. When you look at what is successful in going from experiment and POV through production and where things break down, I'm curious what your learnings have been as you've looked at enterprise rollouts.
Yeah, well, it's interesting just listening to what Neil and Dylan have said up to this point. The internal corporate SLAs that are required for something like a LinkedIn, and then the SLAs that the NeoClouds have, they play a role in upper end enterprise no matter what. And it really is about ensuring that when you get to that full production state, that all aspects of the stack, the AI stack, and when I say AI stack, this is inclusive of every aspect down to the concrete it runs on, the power in the building, the liquid cooling that may be required, the systems, the chips, then the networking interlinks, and then the throughput of the data, and then where you're just at a bare metal as a service. And that's kind of, as you look at certain NeoClouds are just providing bare metal as a service, you keep going up the stack as an infrastructure as a service. The SLAs for internal IT organizations, that's where their minimum bar is. They've got to be able to deliver that to their companies. And if there's inefficiencies in that, it becomes a big challenge at the infrastructure level. But then you go up one layer where Dylan just went, which is starting to get into the IaaS layer, the PaaS layer of the platform. The expectations of the users and the sophistication of those users, they don't care about that infrastructure anymore. They care that it just is available and it works when they need it. And so that when they need it is an unpredictable timeframe for the NeoClouds, for the enterprise IT organizations. And so what we're finding is that you've got to build a resilient stack. And we in our AI and Cyber Lab, we prototype those builds. And we think about where they land is truly just a landing zone. So when that stack is portable, it can run in a CSP hyperscaler, it can run in a NeoCloud, it can run in an on-premises environment. It gives IT now the ability to select the ones that have the best amount of uptime, that solve those problems in the POV, that ultimately deliver back that value to the business. And so when we talk about the AI stack, it's got to go up to the actual app layer. That availability is what those end users care about. And if you look at the end users you're servicing, the data sciences organizations, your software engineering organizations, even your business intelligence organizations, the business outcomes are what the business is investing in. And so it really is a triangle of a buyer. IT operations has to provide that service, whether you're procuring it from an XSP or you're running it internally, and it's got to be reliable or their jobs are on the line. And so that's where we come in and I really assist the IT organization, help make sure that you're managing that matrix and delivering that full stack outcome.
Right.
Because that's the dollars that are being spent. And those are the dollars that, if inefficient, companies go out of business.
That makes sense. I'm going to piggyback on one observation I'd make. If I go back 15, 20 years, the amount of expertise at the infrastructure layers that most companies had was quite significant. Over the last decade and a half of abstractions that have been built into cloud, and as more and more deployments have gone through that cloud abstraction layers, it feels like deep infrastructure expertise is not a strength that most enterprises have. Even many of the NeoClouds that I've talked to are struggling with hiring and having enough skills in that domain. And so part of the question is sort of, as you work with mainstream enterprises, is the skill gap does that mean that ultimately almost all enterprises will see more and more deployments in NeoClouds or hyperclouds? Is there going to be an on-premise deployment model at all? I'm just curious what the skill gap means, or are we just going to fix it by having more people ultimately join this? NeoClouds certainly are already finding, I think, a struggle on how can they recruit, and there are some that are really good at it, but others are struggling with the resources, is what I'm seeing thus far.
Well, if I go back in history 20 years ago, when we started to see the initial stages of what are now the hyperscalers in the world, said, that's the better way to model this. I want to run in somebody else's data center. I'm going to get rid of my data center expertise. And so for the last 20 years, there's been a brain drain and there's been a graying of those that are in that space to be able to optimize that infrastructure. But now when you look at the economics of this, these are 10x economics, at least from where they were 3 years ago, because the importance of frontier model design, frontier model utilization, implementation of agentic process, we're starting to see that become now a critical business. I'd say it follows the data. Where is the data? And in most cases, that data still sits in corporate systems of record that sit in the data center. So that skills gap is really critical. The NeoClouds become a very great way to essentially extend that towards the edge, but there is still that need for a hybrid plane and the management across that. I think the NeoClouds themselves are also starting to specialize. I mean, I love your point of view on that, Ellen. For me, that the specialization starts to go down to, are they specializing by industry? Are they specializing by workload? Are they specializing by inference versus train? That's where I think the IT operations teams of the world today need to focus on what are we trying to accomplish with this workload management using an AI workflow, and then you'll see where that skills gap has to be filled. Yeah. And it is a race. We're we're starting to really drive up the we're pulling straight out of high school in some cases, out of some of the top end colleges to fill the gaps for our ranks that we're helping enterprises with. But the enterprises themselves are fighting for those same resources. And so the NeoClouds are, again, a very nice middle ground to allow for those workloads to scale, prove your POVs out, and then validate and move into full scale.
No, that makes sense. That makes sense. I have to say, Dylan, you mentioned ClusterMax. I've read in great detail the ClusterMax 2 version that came out. And for anyone that's deploying AI applications, or definitely if you're deploying AI infrastructure, it feels to me like it's absolute must do reading. So we talk about utilization ranging between 30 to 55%. And as you look at the various attributes that are encapsulated in ClusterMax, if I were to ask you to say, what are the top 3 to 5 things in a Pareto manner that take away from utilization and land you in that zone? I'm just curious, based on your experience, what are you seeing as the top 3 to 5 things to pay attention to?
So I would say many organizations end up being subscale, and so utilization is always going to be a challenge when you're subscale. Right. So more so referring to skilled organizations where they still have poor utilization.
Indeed.
Right. And there's a few things that I would say are really critical. Right. One is that you have significant numbers of failures of GPUs. And as these failures happen, your entire workload, you might have, hey, I'm running a job on 64 GPUs or 256 GPUs of my 500, right? All of a sudden that fails, that moves out of the queue and Slurm, and then some other jobs that are 64 and 8 go, and then you're like, okay, well, now I'm going to reissue this 256 job, but what do I do, right? It's I can't fit it, so it's a jigsaw puzzle, and I'm already using, I only have 192 GPUs idle, but this 256 got reissued. And it's going to load from a checkpoint. It's like, okay, well then I'm idling a huge chunk of my cluster.
You've lost time and you have scheduling problems, right?
Right, and this is happening always. A lot of companies have, even these small scrappy, companies or enterprises or startups end up having to hire 1 or 2 people overseas, but then finding someone overseas, whether they're in Europe or Asia, just because they want to watch the runs.
Right.
And if something fails, then someone needs to reissue it. It's literally a job at many of the AI labs, even the major ones, to watch there is a night shift, right? Which you would think is crazy for these people that are making.
Speak about automation with.
Yeah, because there's just so much, right? It's like it fails, but then you might need to tweak the job. So the reliability of GPUs is a huge issue. It's one thing if a GPU fails, right? That's a catastrophic failure potentially if you don't have fault tolerant libraries. Another set of things is how do you do the cold swapping, hot swapping with regards to reliability? Another issue is power and thermal, right? It turns out there are significant challenges with hitting peak flops on a GPU. In fact, it's physically impossible to get 2,000 teraflops out of an H100, even though NVIDIA advertises it. At most, you can get 1,300 of FP8, floating point 8-bit teraflops. So that's if you're just running matrix multiplications over and over, and you're not actually running a workload. If you're running a real workload, it ends up being like 700-800 if you're really, really good. So your utilization has fallen so much, but a lot of that 1,300 to 2,000 gap is thermals, and that gap from and so if you're thermally limited anywhere, if you're waiting on data, whether it be storage, CPU, memory to send the data to the GPU, any of these things can drop the utilization down further and further, which gets you all the way from that 2,000 peak or temps all the way from that 2,000 peak all the way down to a 700-800, and that's a best case. Right. In reality, most users are getting lower than that 700-800 because they are not writing custom kernels and hand tuning everything. Right. They're using Torch compile, or they're writing some Triton. It's like very, very simple. And then the last sort of thing I would say is on the reliability point is the blast radius of failures. And sort of going back to the first point is the blast radius of failures is really important. Right. If you have an 8 GPU server, 1 GPU fails, you've lost 8.
Right.
But if you have a 72 GPU server, 1 fails, you might, if your workload is relying on all 72, you've lost all 72. And what's even more important is if you lose a network switch or an optic, there are so many of those in a system. If one of those breaks, if it's a network switch, you might lose, hundreds of GPUs.
All the jobs at the same time.
Yeah, or all the jobs if you're not intelligent about it. Or you may, if it's just one single networking transceiver, but you have a network of, let's call it 10,000 GPUs, you may have 30, 40,000 transceivers. And if one of those fails, and their failure rates are just as bad as GPUs, if not worse, then and your workload's not smart enough, you may lose, an entire node or an entire job, which is running on hundreds of GPUs. And so these are some of the things that cause a lot of the performance issues or utilization issues is reliability of GPUs, reliability of networking, both switches and transceivers, and then the entire aspect of, hey, my temps are bad, or my power is not being delivered properly, and then lastly, sort of what's going on with feeding the beast, right? As Suresh said earlier, your networking, your storage, your CPUs, your memory may be bottlenecking you.
Fantastic. That is a great framework, and actually, it's a beautiful segue, because when we first engaged with you, Neil, at one of the reasons Clockwork was interesting to LinkedIn, and sort of what drove the deployment was our ability to survive link flaps or failure of a link between the GPU and the Tor switch, and continue training even when those failures happen. And then you yourself have been passionate about it's not just about network failures. Something we're working on together is the ability to actually continue training in a non-disruptive fashion when GPUs themselves disappear. So I'd love to hear a little bit about what did that mean for LinkedIn? What was the impact? What was the pain point?
Yeah, I think when we got engaged with Clockwork, it was very specific, these flaps or, some of the architectural problems where ranks mapped to Rails or NICs. And if you had a failure on one of those NICs, it meant the jobs which were running on that would stop, and you didn't know what to do. I think that was the use case that we had got involved with Clockwork, and that solved the problem by being able to route it to a different NIC and make sure that you take out only capacity of 25%, and now you could utilize all the GPUs even though a NIC was a failure. I think as we deployed that stuff and went more under the sheets, I think the other offerings that Clockwork brings to the table is like the network congestion, flapping. These are, when you talk about GPUs and clusters of 1,000 and 10,000, 50,000, trying to manage that stuff is like a nightmare. It's like trying to fly a plane through a storm without any telemetry or any of that stuff. I think what Clockwork brought to the table was providing us that telemetry, that visibility into the network congestion and being able to route stuff. Now, could we build stuff? Yeah, but it's going to take funding, getting engineers to work on that. These things take a long time to get deployed. So I was very passionate, and I'm still very passionate. Like, I would want to use Clockwork across the networks. My thing to a lot of the cloud and Neo guys who are building now, deploy this from day one, because trying to solve these problems later on is a pain point. It's a real pain point, having run data centers and networks for 15 years. there's always a problem like, hey, a job fails, they'll say it's a NIC problem or it's flapping, and then you go into these postmortems. So I think getting that thing done is I think everyone should deploy it. The other bigger thing which I really also loved, and and as we had a conversation about non-disruptive moving or migration of workloads, if you have to run these things, like these things you deployed, it's on your books for 6 years, it depreciates over 6 years, you got to manage this whole ecosystem. You have to do a lot of maintenances on it. You got to do security patching. You got to move workloads around. You got to move sometimes servers because you're retrofitting the data center, the data halls. All these things need you to be able to move your jobs and your workloads seamlessly. Anyone who can provide, and I know you guys are working on that stuff, who can provide a way to non-disruptively move workloads is going to be a great opportunity for us, for reducing downtimes. And as Dylan mentioned, these things, you cannot afford for a job to fail.
Right.
And rerun the jobs, because the next time you rerun it, you don't know whether you're going to be able to run them and you're going to get a slot to be able to run them. So I think allowing for non-disruptive workload and migration of workloads is going to be really a needle mover, I think, for a lot of clouds, as you have to maintain these things over a period of time.
No, indeed, Neil, we are very excited. The link flapping solution was something that we saw a lot of impact from, but we're working on how to transition that to non-disruptively moving workloads when you have other kinds of GPU failures. And we think that, you've said it eloquently, both of you have said it, it's a big pain point. I think you raised that as the number one factor when I asked you, Neil, what was impacting utilization. And so that I'm excited about. I want to ask an architectural question. Maybe a lot of this has been around operational, and maybe two actually questions. One, Jack, you've had 7 years at Pure as a technologist driving a lot of the Pure Storage deployments, and you're very passionate. Even when we chatted earlier, you were talking about data as the fuel, communication networks as the fuel lines, and of course the ultimate consumer is the factory, right? And so you've talked about data and architecting data as you build your AI infrastructure as a big part of how to make AI infrastructures efficient, but also sort of overall get more out of the training models, I suspect, and so on. So can you tell me a little bit about what are the challenges in building a good data infrastructure surrounding your AI factory?
Yeah, well, so I mentioned it earlier that where the workloads land is where the data is. And it's because the data is that fuel, but data lives in silos across different separate types of data. In some cases, you've got S3 buckets running in hyperscaler clouds. You've got NFS shares that are your archival tiers. You've got block storage that's there as your primary system of record. And all of that data needs to come together to add the proper context to whether it's model design or inference utilization or multiple agentic processes across that. So to have a resilient data layer, not storage layer, not memory layer, but the data itself is very critical to allow those pipelines to ensure that the jobs aren't waiting when the scheduling comes up and is available. And so having a resilient network that is ultimately running across different protocols, RDMA, straight Ethernet or InfiniBand, those are very challenging to architect a seamless system that can then be ingested into that processing layer that now sits at the GPUs. And so it's very critical that you've got a data strategy that allows you to span that, because in a large amount of this, you're not looking to actually process the core data. You're looking to process the metadata that sits within that data. So in a lot of cases, you don't need to move the data. You just need the metadata to process that fuel. And so that will keep that innovation curve going. And I think we're just starting to get to that layer of global data estates becoming very, very critical when you talk about running them across multiple landing zones, being able to have that seamless utilization, whether it's inside your corporate estate, inside a NeoCloud environment, or inside of a cloud environment, or across all three, having that data layer and having a resilient data layer. Because when you've got to go back and checkpoint these things, maybe you're up in the KV cache layer and you've got to checkpoint these, the impact of that downstream in your data layer is important. Do you need to do data refreshes? How fast are you, if you're doing refinement or fine tuning, how fast does that data need to be processed back in for your next checkpoint and the fine tuning elements of that?
No, that makes sense. I guess you mentioned the context of course, bringing data from multiple repositories. But along the way, you also talked about the feeder lines incorporating Ethernet, RDMA, InfiniBand, etc. So when Clockworks talks about its theses as software-driven fabrics, our longer-term vision is that AI has caused a proliferation of network technologies. You have GPU to GPU communication necessarily going over RDMA fabrics, whether it's InfiniBand or RoCE v2. You have, of course, front-end user-facing application logic flowing over TCP, certainly in inference architectures, but even there's some amount of TCP even during pre-training. And then you have storage where it seems like some people will deploy storage over TCP networks, over front-end TCP networks. Others are looking to accelerate the flow of data into GPUs by using sort of RDMA networks and using technologies like GPU direct storage, etc. On the one hand, this is all geared towards making your factories process faster and faster and faster. On the other hand, the network technologies are getting extremely complex. So diving a little bit into the communication side of the house, our thesis is that longer term, a software-driven approach will allow you to, and as Ethernet becomes more and more accepted, that you'll start to converge the fabrics and use software to partition them, guarantee quality of service. So you of course don't want to delay your nickel operations on the back-end RDMA network, but that can be accomplished without physical segregation. I am just curious, all of you have had experience with networking over time, and I feel like every time you bet against Ethernet over the long haul, it wins. So I'm curious how you would think about this, and maybe Dylan, ask you. It's a provocative long-term vision of where we think we are going and where we think customers will want to go. Does that make sense? Any comments on that?
Yeah, I think initially in the AI race, especially around early Hopper days, anyone who didn't deploy InfiniBand was putting performance on the table,
Right.
And was not feeding the beast, right?
Right.
Which I'm totally stealing.
I love this feeding the beast. That's a meme from here now.
Yeah. So and this is evident if you took GPUs that were at Microsoft versus Amazon or Google, there was a massive performance difference. As they didn't want to deploy InfiniBand, Microsoft was like, you know what, I'm just going to deploy InfiniBand. Over time, Microsoft and Amazon have been able to improve. They've tried various tweaks to their network protocol stacks, not even using regular RDMA, using things like their Falcon GRD or using things like EFA. But as you step forward, Ethernet has been tuned to the point where there's so many people working on Ethernet that actually now Ethernet is similar performance. And even NVIDIA themselves, the vast majority of the systems that they quote for Blackwell are Ethernet based. Now they're NVIDIA special Spectrum X Ethernet, which has certain unique properties around how they chop up packets, how they spray packets, how they do congestion control. But at the end of the day, it's Ethernet, right? And so whether it's NVIDIA doing Ethernet, or there's larger and larger percentage of customers doing non-NVIDIA networking solutions with their GPUs because they don't necessarily have to just buy the sort of big iron thing. They can start to pick and choose what they want from NVIDIA versus others. Whether it be for cost savings or performance or supply chain security, there's more and more diversity, and Ethernet is going to be the mainstay, right? And you can see this with even the major labs, right? All of OpenAI's cluster deployments in 23 and 24 were pretty much all InfiniBand.
Mm-hmm.
Now with their Stargate projects, they're all Ethernet. And the same applies to other folks, right? Meta earlier on actually deployed a large Hopper GPU cluster with InfiniBand, and then they moved to Ethernet. Elon Musk's world initially was InfiniBand with Tesla, and then they moved to Ethernet. And with XAI, they have one of the largest clusters in the world. It's Spectrum X Ethernet, right? And so different customers are going, whether it's Spectrum X based Ethernet or some Arista or Broadcom Ethernet. But the answer seems clear that everyone is going Ethernet. And there's many things that you can build on top of that Ethernet stack that maybe you couldn't have on top of a proprietary InfiniBand stack.
Makes total sense. This is actually maybe the picture you're painting is one of maybe even greater acceleration than we working day in and day out in the communication side of GPU clusters or maybe seeing, because when this may be a faster pace, because when you paint the picture of what it was like 2 years ago at these leading sort of leading edge thinkers and deployers, it's a matter of time before that percolates everywhere. So that's interesting.
And that's really true, because that's something that we went through similarly. Initially, when we came out, my networking guys wanted to go with Ethernet. I was like, let's not do that stuff. You're paying this, it's cost us so much. So try to test it out. Going with Ethernet is the wrong thing right now. So when we started deploying GPUs, we went with InfiniBand. But as it's matured, I think the industry is now moving to like, hey, let's go to Ethernet and let's try to do something different. And especially with all the tuning which is happening. So it's definitely, there's a paradigm shift and shifting in that direction. And I feel maybe at some point, NVIDIA may probably come out with a different approach in terms of how they position InfiniBand as well.
Right. Well, and I think it's a fact that at least looking back over the last year, SpectrumX, I think from publicly reported figures, even for NVIDIA has grown faster, now off of a smaller base, but grown faster than InfiniBand has grown, as I understand it. And in particularly recent deployments, it's now equal footing in terms of share. So that's already a suggestive of this kind of shift. Maybe the second part of this question that I'd love for you all, you were early in embracing RDMA capable NICs across your entire infrastructure. Neil, as I understand it, LinkedIn's you started by embracing RDMA capable NICs even for non-RDMA traffic. We talked a little bit about storage moving towards RDMA as well since we're using this over and over again to feed the beast faster, if you will. I'm just curious about this network technologies moving towards Ethernet, and then there's the protocol layer where you want to move towards using RDMA capable storage protocols. Are you seeing an accompanying shift in how storage is deployed from TCP based storage towards maybe RDMA based storage, whether InfiniBand or Rocky for a moment? I'm curious for all three of your takes on this.
Yeah, we've been kind of looking at moving to RDMA for storage because we were building our own storage layer. And I'm a big philosopher about, my philosophy is like try to economize the cost and deploy it across the network. So you don't have these small islands like, oh, I can only run this workload over here because it has, NICs which support RDMA. So that's something that we had adopted much earlier in the game, got the cost down as much as we could, and then started deploying it across all our servers. And the driving factor for that was more because I wanted to provide managed disk as an offering through LinkedIn. I think that was my big thing. And as subsequently, we've kind of built other storage systems on top of them and all of using RDMA. So that was a good strategy when we started off. It's now paying its dividends as GPUs coming around and needing to pull up, pull access storage at a much faster speed with low latency. I think it's a strategy which kind of worked out, and that's something which I've always been ahead of the game. We might make some investment, like our network might be over provisioned on other areas, but it's the cost that you have to pay for deploying it in the servers up front, as opposed to going and retrofitting your network later on, is much more expensive. So that's been my philosophy, and that's kind of working out well from a strategy standpoint.
Interesting.
Yeah, from my former role at Pure, I think we absolutely started to see Rocky V2 become a default from high throughput, high performance computing. I think use that very specifically. Kind of pre-AI high performance computing has been around for a long time, and RDMA Rocky V2 has become really the de facto standard for that, the network for storage. But in reality, these GPU clusters now that are now requiring high performance NVLink, the ability to manage the memory, the shared memory spaces, and then your management layer. So you've really got three networks that still exist today.
Right.
Two of which are speaking traditional Ethernet. Of course, you can layer in, of course, SpectrumX and some of the technologies that NVIDIA is getting behind, and even others like Cisco are starting to really kind of embrace together. But you still have these three different layers. But the other side of that is you also have skill sets. I go back to this gap of 20 years of moving out of the data center. The individuals that know how to operate Ethernet networks are the same ones that are running those RDMA networks as are running your core management layer networks and your traditional kind of networks that have to be up and running from observability and management, job scheduling, those sort of things. So you've got a good skills management there, but it's that InfiniBand layer or that the NVLink layer that needs that convergence. And so I think that some of the things that you were all working on is really, really interesting to be able to really maybe potentially collapse those networks and keep the management with those that have those skills,
Right.
while also driving up the reliability, the uptime, the throughput, the management, feeding the beast consistently.
Perfect. What are you seeing, Dylan? Are you seeing a trend towards RDMA storage in GPU clusters? Is there any discernible pattern that you're starting to see? I'm curious about.
Yeah, there's initially high performance storage was useful just for checkpointing
Right.
and loading data. But as we've moved forward from there, there has been an increasing need for high performance storage outside of just that, including in inference. Just like initially inference was fine with, hey, I don't actually need an RDMA network for inference. I can just rely on just the front end.
Indeed.
And as time has evolved, that has changed, right? So when we look at what does a modern high performance inference system look like, one example is one that DeepSeek open sourced over December of last year / January, February of this year, where a single replica of inference for a single model is going to be like 140 GPUs, right? Those GPUs all could talk to each other over RDMA backend networks. In addition, they'll offload KV cache, i.e. the context, to either to the CPU memory or the disk, right? And they've described all this in detail. And as we see more and more, people are, in some cases, they're using a separate RDMA NIC to offload traffic, to offload a lot of this KV cache out of that one GPU node into a shared repository of shared KV cache. So when you have repeat calls, you don't have to recompute everything. You can actually just call in that KV cache. There's some load time associated, but it's much, much cheaper than recomputing the entire context. That's in some cases, and in some cases now you even see people putting storage directly onto the backend RDMA network, right? Where hey, I can now feed the KV cache to a given GPU node at 3,200 gigabits per second.
Right.
And so that is starting to bring a lot of complexity, right? Whereas in the pre-training era, all the networks were, it's basically, you knew when all those communications would happen. Hey, this layer happens, this GPU talks to these GPUs, this all-to-all happens, this ring reduction happens, whatever it is, you knew what happened before you clicked go on the job. You just knew what was going to be there. Now you have this high variability system where, certain users are hitting KV cache over here and they got placed on this node, so you're going through here, but at the same time, the GPUs are sending data to each other and you don't know what expert's getting routed to what expert. So traffic is just bouncing all over the place and that makes it much more unpredictable. And RDMA for storage and RDMA for GPU to GPU overlapping each other is very complex and you need something to be able to manage that, right?
I think this was
I think one of adding to some of that stuff was basically going to these provisioning bigger NICs and even though it was ahead of its game. I think now one of the projects that I was kicking off was QoS at the network level. I think something that Clockwork's been talking about.
Indeed.
And I think if you provision for something, over provision, you can at least use these QoS to kind of to prioritize RDMA traffic for storage for the GPUs better. And I think that is like future-proofing your network to be able to programmatically make these changes on the fly and kind of leverage that stuff. And I think that's a great, feature that you guys are looking at integrating into your software, which I think will allow these cloud, NeoClouds, and even the hyperscaler guys to be able to utilize the network better. Indeed. Without having these special networks and separate NICs.
No, indeed, I think in the long term, we do believe it's I think, problem when you marry the two constructs, right? The ability to be able to segment the network and make sure that one is not trampling on the other, particularly in the face of what you said, higher unpredictability, especially with inference deployments, and inference deployments, which used to be predominantly just front-end network driven, but increasingly requiring RDMA networks because of KV cache offloading to storage over RDMA, disaggregated serving. All of those are driving, I think, sort of a more complex networking that I think, so that's something we are excited about, what we're working on from a software perspective to manage those flows and segregate those flows and not let one trample on the other. I realized there was a whole discussion that I wanted to drive on inferencing and architectural implications of inferencing, but this has been such a fascinating conversation. I'm going to try and distill this down to maybe if you had each of you, if you think about what is the one recommendation you would make to someone who's a large-scale GPU cluster operator to have ultimately impact their ROI and raise efficiency? I feel like from what you've all described, each of you has a pet topic that you'll touch on.
There's
but
no
just
gun
one
against
comment.
our head. We're all going to say buy clockwork.
Well, that we appreciate very much, but I'm curious what it is that sort of you all think is the area to focus on, and I really appreciate that one. But each of you, I'd love to get your topics.
Well, I'd say from our side, especially, at the enterprise level, you have to have that observability, and you have to have that ability to know what your true utilization is. I mean, I think, Dylan mentioned some numbers earlier of like, that's effectively a 30 to 30.
I know, I just realized that what Dylan said.
Utilization
Yes.
of a GPU cluster that you've just gone and spent tens of millions of dollars on. And so just observing that is important.
Right.
But then what do you do about that? How do you ultimately identify which part of the layer needs to be improved? Is it, model context and memory? Is it throughput of, RDMA network? You have to have a system that's capable of really observing everything that's going on. And, to put the plug in for a clockwork on this, you guys have a system that allows you to look at that in a very, very unique way that is very critical to drive that utilization up. I mean, if I was running any system at 30% utilization in my former role as a customer side CTO, I would have lost my job. So I think it's very, very critical to have that observability and that ability to at least identify where the bottlenecks are and then address them piece by piece. And if it's reliability, when these listen, there's physics involved at this that the average IT operations manager hasn't even thought about. But link flapping due to poor optics is one of the major problems that exists. Reliability of the GPUs themselves, I think, falls into a second there. But just being able to identify, okay, this is a node that's showing, or this is a link that's showing flapping. Can we proactively manage off of that and put in a maintenance cycle for just that node, or just that optic, or just that GPU node? Now all of a sudden you've given you the tools of not just having observability, but now the ability to manage those workloads and then optimize those workloads automatically. So to me, it's a really, what you guys are working on and what you guys have deployed already is very important to drive that utilization up, right? Continue to feed that beast, not just the storage, not just the network throughput, not just the GPU utilization, but the whole thing. That full stack is very, very critical.
Fantastic. So observability is the first step to really getting it up, is where you would, and that was very well articulated. Dylan?
Yeah, I think piggybacking, right, that which gets measured gets improved. And it's not just on the infrastructure reliability layer, right? There is this whole layer here of infrastructure hardware, right? Application or infrastructure software, and then application software. So this hardware software co-design must happen, right? Whether it's the software telling you when hardware is failing, or the hardware being equipped to make software much more efficient. Today, everything is, at least historically, everything has been very much, brute force, right? The scaling laws promote us being brute force. The better lesson is us being brute force. But there's a lot more intelligence you can get out of this by not being brute force always, right? One of the things I mentioned in the last sort of question was, hey, how do I offload KV cache? How do I prevent the processing of data that I don't need to process?
Mm-hmm.
And when you look at production systems for inference, for at least for certain workloads, but a lot of the workloads that we've been tracking, your input-output ratio of models ends up being, hey, I'm inputting 30,000 tokens and I'm getting, 2,000 to 4,000 out. And that's a very common ratio, right? And then when you think about, okay, the cost of running prefill is roughly 1/4 of running decode. So then that 30,000 tokens, that prefill, that 30,000 tokens still cost a lot more than that output. So right. you can cut your cost to 1/4 of what it was previously if you just don't do the prefill, right? And now that involves a system that you can observe, that is reliable, that you can have a converged RDMA network across both GPU to GPU communications as well as storage. That's all a prerequisite to deploy this, 4x cost savings on large scale production inference. And if you can do that, now you're not brute forcing work. You're actually being intelligent with how you've done the hardware software co-design. But to be able to do that, you must be able to deal with, hey, reliability, hey, converging the backend network and storage, hey, what's going on with regards to link flaps, I must be ready for the high variability of the network. These are all prerequisites to being able to deploy that solution. And so if you can do that, then you can get this 4x plus cost savings.
Fantastic.
I would say, being the net infrastructure guy, I'll probably take the infrastructure stuff. I think thinking about these things for long term. Data centers, it's on your books for 10 years and you can increase those leases. Thinking about how you're going to do cooling, and I know it's already spoken for, like a lot of the NeoClouds and all are doing a good job on that stuff, but like rack density, what kind of rack, are you going to future-proof it? Are you going to do for 130 kW, but Ruben is coming out, which is breaking that stuff. So if you install and you make these investments, it should be future-proof. So I think that's one thing I would say, thinking about that. Next thing I would say, looking at your network, is your network going to be fungible? Are you going to be able to use GPUs when someone is using it for running these big jobs? Can you use some of that for inference at the time? So you're basically maximizing the utilization. So that'll depend on how your network is configured. Do you configure them in security zones, or do you make a flat network where you can make it fungible at any time? So I think that would be another thing to think about. And then, obviously future-proofing in terms of NICs, like do you over-provision, pay a little more cost now, but you don't have to retrofit and throw out the gear. So that's something I would say you got to look at. And then the thing that is operability, is getting the talent to run these things. You're making such investments in the gear, data center technicians. You cannot just get anybody who knows how to put a cable in there. You got to have someone who understands what it means to a job, and that's raising the bar in terms of the talent that you need, networking talent that you need to run this stuff. So I think it's just looking at it holistically and kind of looking at it from that standpoint. I think what Jack mentioned about observability and what Dylan mentioned, I didn't want to go into that stuff because they don't.
It's well articulated.
Those things can be fixed because they're software. These things are physical. Once you make it, it's going to be there for a long period of time, or you're going to have to write off your books, which I think some of the Neo guys who are made some bigger investments in those areas and are not there anymore.
Well, let me just use the last 2 minutes to conclude. I just want to start by maybe just the 2-minute synthesis here is we are spending hundreds of billions of dollars, hundreds of megawatts, soon tens of gigawatts on infrastructure that is operating. It seems like even my 30 to 55% was generous, but somewhere in the 30 to 40% zone in terms of utilization. That will change. And you all were extremely insightful in calling out some of the big factors. The themes I heard were reliability takes away from utilization in a very fundamental way. Themes I heard were a lot of the time spent on networking, feeding. We kept talking about feeding the beast, which is really optimizing the communication or the fuel lines to the beast, the communication networks, optimizing how storage is delivered. But also we talked about co-designing sort of systems from the hardware, infrastructure, and actually how is the model working, how is the inference serving working, and how do you optimize up and down the stack with deep observability, not on any one component, but end to end, so you know where to focus your optimization efforts. We're driving this. And lastly, making sure that you're future-proofing your data center design, whether you're a cloud operator or an enterprise that's choosing to deploy your own infrastructure. All of these were elements that led to sort of the poor utilization and what to do to correct it. So extremely helpful. I just want to thank our audience for joining us today. I'm hoping you found this all very useful. I'm extremely grateful for the time from all of you. Thank you very much. Really appreciate this.
Thank you.
Thanks.